Good afternoon. My name is Ari Vanderhoeven. I'm a principal project manager with Seagate. I'm here today with Tim Walker, principal engineer and technologist with Seagate. Tim has spent many years in this type of topic, and the topic today is unleashing the performance of multi-actuator drives. Let's look at the agenda. We're going to start by looking at what we're calling the multi-actuator era. And that's because we're getting to a point where drive sizes and areal densities are becoming so large that to achieve any kind of reasonable IOPS performance out of a device is going to eventually require multiple actuators. So we see that starting today, and we'll go into that more in this first section. We'll talk about developing for SAS, which is in market today. We'll also look at SATA, which is the next step in multi-actuator drive adoption. Tim will go into a lot of detail on deploying SATA multi-actuator drives, and he'll give you some performance guidance on what to expect and how to prepare. You'll leave knowing how to deploy systems to take advantage of multi-actuator performance. You know, this is really about what you need to start thinking about today for actual work you'll be doing in a year from now, 2 years from now. You need to be also looking at the stack, preparing applications and workloads and your storage stack to take advantage of different types of multi-actuator environments. So the multi-actuator era, and this is a quote from Senior VP at Seagate, Jeff Fachman, and he was referring to this next slide when he said that all that data cannot sit behind a single actuator. And if you look at the progression of drive capacities, you know, he's looking over here at 30 terabytes plus, 40 terabytes plus. You know, you're at a point on the right here where the size of the drive and the physics just cannot maintain the IOPS needs of a typical application, nearline or enterprise and other. So we see this transition from an era of you know, where today 14 terabytes dual actuator is a niche product, very important for some high performance applications, and we see that changing rapidly as we move forward. So the challenge is maintaining performance density, and you know, we have to be able to maintain this trend we have, this great trend we have of having larger and larger disk drives, price erosion, and better TCO numbers. And the real barrier is IOPS. You know, how do we keep up the performance needs of our baseline applications? And you know, today you see a lot of work going on. You know, the first one I'll call out is caching. You know, up to about 10% of your storage mix being flash gives you significant performance boost. Beyond 10%, there's diminishing returns. Queuing, you know, managing going with deeper queue depths as long as you manage latency carefully. IO prioritization, we see command duration limits now as an important technology, and a lot of work going on in standards and Linux and in the ecosystem around that. Longer transfer lengths, and then just innovations in things like IO schedulers. You know, we're also talking about the BFQ IO scheduler work for specific to dual actuator, but there's other performance work going on, file system optimizations, asynchronous IO, and work going on in Linux and Windows. All that's great, and it's very needed today. And you see this activity for a reason, but at a certain point, you need the raw servomechanical capability of two actuators. So the solution is multi-actuator technology. This comes in, you know, we'll look at it today as three flavors: multiple LUN SAS or dual LUN SAS, as we have today, SATA, and also single LUN SAS, which is a need that some customers have asked for anyway. And you know, this gives us up to 2x performance, and it really does in many scenarios, because you have two independent actuators who are transferring data concurrently and are overlapping. So that's just a very simple key technological advance. It allows us to maximize drive capacity, so we can start deploying these larger and larger size drives. And today it's built for applications that really need performance, you know, mail servers and content delivery networks that have really high IOPS need. We see that moving into software-defined storage, into S3, Ceph, Hadoop, you name it. We expect this to become, you know, for performance today, but more mainstream nearline enterprise tomorrow. So Tim will go into a lot more detail later on performance, but at a very high level, the two areas where we excel. And the first is, we have independent actuators that are providing parallelized random access that's very good for random I/O at lower Q depths. And then we're implementing independent read and write paths to allow simultaneous parallel transfers for sequential I/O with these larger transfer sizes across all Q depths. And this allows us to manage power and to minimize the impact to existing infrastructure. And these are really areas where we see sweet spots for where the need is in the ecosystem for performance. So it's a very tuned solution. And the next thing we look at is power efficiency. Because you have two independent actuators at a per drive level, there's higher power consumption. But if you look at it in terms of IOPS per watt, you see a dramatic improvement, 54% for random read performance efficiency, 26% better IOPS per watt for random write performance efficiency. If your options are to deploy a dual actuator drive or two single actuator drives at half the size to maintain IOPS, your power savings are going to be considerable. So are your TCO savings, of course. The flip side of this is, if you're a system builder, as you project forward, you need to take into account for these higher power envelopes of these drives. Let's take a quick look at the SAS interface. This is what we're deploying today with our 14 terabyte SAS Exos 2x14 with MACH.2 technology. It's a dual lum drive. Pretty simple. You've got one file system per actuator. You can address them independently, run workloads independently. And in the Linux view, it looks like two separate devices. Just need to make sure that you're keeping both devices busy, and it's very easy to maximize performance. But there are other ways of implementing. We just talked about how you can treat each actuator like an individual drive with dual on SAS. That's really your highest performance potential. We can get close to 2x performance in many scenarios. The user has complete visibility and controls the movement of data. Do need to make sure you keep each line actuator busy. And if you're deploying SATA now, SATA has a single contiguous LBA space, so you'll need to partition if you're going to treat it like two separate drives. And Tim has details on that later in the talk. You can also span both LUNs into one large volume, which is what SATA looks like by default with its single namespace. Here, the user doesn't have to manage these separate LUNs or actuators. It's good unless you have IOs that are crossing IO boundaries, or you overload, disproportionately send IO to one half of the LBA range, then you have an actuator that's starving. It's not doing its job. BFQ, the innovations in BFQ that we're working on help address that. But there's more to think about if you're deploying as a single large volume. And then a third solution is striping. RAID 0 striping. You can have all these stripes. Theoretically, your workload should be balanced across both actuators. The downside is striping affects performance and latency. There could be operating system overhead managing the stripes. This is probably the least performant solution of the three. It's another one we're looking at. And finally, let's look at the SATA interface. This is what's new and coming next. And you have this single contiguous address space. Much of Tim's talk, which I'm about to hand off to, will go into how to deploy and the performance considerations around SATA. But now you have these two LBAs. There's work going on in the Linux community to expose these address ranges. So perhaps at the OS or application or file system level, you can now see two drives and address them independently, but there's a lot going on here. And with that, I'm going to hand over to Tim Walker for deploying. Thank you, Tim.
Well, thanks for coming to our little talk. My name is Tim Walker. I'm a principal engineer. I work for Seagate Research. I've been involved with multi-actuator from the very beginning. I really believe in the technology. I've seen it deliver some really nice performance on the hard drive scale. So next slide, please, Ari. we got a lot of lag in our system as we're recording this. So we're gonna try and stay synchronized so none of us get too out of sync. I got a kind of a simplified diagram here of Linux storage stack. And some of the ways that we look at handling multi-actuator in the case where we're using SATA or a single-run SAS drive. You already saw the first dual actuator drive that Seagate released was a SAS device, and we had a logical unit permanently configured for each actuator. And they're totally independent. And under Linux, it shows up as two devices. Even though it really is only one device underneath. And there is some ramifications from that, particularly on queue management. But with SAS, the queue is so deep that it really never became a real issue. But customers have asked for SATA interfaces for cost reasons and asked for single-run SAS for ease of management. And so we've had to go back and look on how to do the workload management outside of the drive, where it's not automatic like it is with the dual-run SAS approach. Next slide, please. Here it comes. Okay, where can you do what? Where can you manage the workload? Because our goal with the dual actuator drive, since on the dual actuator drive, on the Seagate design that we've been talking about this afternoon, the actuator is pretty much sawed in half, and the upper half of the actuator addresses the upper platters, and the lower half of the actuators address the lower platters. None of the media can be accessed by both actuators. So any particular piece of data that you write it on whatever actuator that is handling that sector is the same actuator that has to read it. You can't write to one and read from another. We have to keep both the actuators busy. In the case where all the IO is going to only one actuator, the total drive performance is going to be single actuator performance. Our goal in working with our customers in implementing the multi-actuator drive in their system is not so much to redirect the IO to balance it, but to make sure that the customer has the visibility and the knobs to control the destination of the IO so that both actuators stay busy. That you can do that at the top, you can do that at the application level, especially for customers who consume storage directly, who not necessarily through a file system. The file system is another place where we can modify the allocator to balance the allocation across the address space. We haven't pursued that really at this point. It seems awful complex and variable, with the potential of side effects and imbalance, and how does the file system really have the knowledge to allocate efficiently across the two actuators to keep them busy. Our approach on this really has been for active intervention, like in a file system case where you're asking the file system to decide where to send it. It's been low on our list of priorities because of the difficulty of the file system knowing what the client's real use is of the file system. Whereas if you do it at the application level, the application knows. If we go down one more level, now at the Devicemapper level, no longer are we even thinking about actively redirecting. At this point, we're talking about exposing the actuators so that a file system or application can know which actuator an LBA is destined for and send it to where it wants to go. And then below that, we can always do something simple like partition the drive and set the partition boundaries on the actuator boundaries. And then below that, we have the case where the scheduler comes into play. The scheduler naturally, excuse me, reorders the commands and groups them for efficient operation. And then schedulers are designed for single target, single actuator devices, will not necessarily reorder or stage the commands in the most optimal sequence. And finally, in the SCSI subsystem, again, we have not thought that this was a place to pick up a lot of gains for managing the dual actuators on the single address space. A lot of this on a stack like this and methodologies, and to present this slide to people like you who work in this all the time, there's a lot of I'm sure there's a lot of ideas already. This is a lot of opportunity for innovation up and down this stack, particularly for in cases where the use case is pretty well defined. And for a large CSP or an organization with a high level of storage engineering capability, any of these levels, anywhere in here is available and can be beneficial for managing workloads across actuators. I'm just like those same kind of organization manages workload across multiple disks on large storage arrays, etc. And on a case-by-case basis, you could go anywhere on this diagram, and probably you could on a case-by-case basis. There's multiple places in this diagram, even though I said, well, we're not going to be in the SCSI subsystem. It's not that it would never be the right place to do it, but at the generic, general purpose storage, general purpose compute approach, at this point, we don't think that's the place to be. Next slide. Here we go. So we're going to talk about the IO scheduler for a minute, because for a couple of reasons. One is that there's another presentation somewhere else in this meeting about the work we've done with BFQ, the plug, as a scheduler to prevent LUN starvation or prevent actuator starvation. But I want to talk about why an IO scheduler is a target for us on managing the workload to particularly a SATA drive. And we know Linux controls queue depth kind of indirectly, and by limiting total number of commands out to the drive. And we also know that good IO programming, the goal is to group and sort IO commands to maximize the locality, to keep them as close together as possible, and to maximize the sequentialness for HDD workloads. For flash, this is not as important, but for a hard drive, we want to minimize seq lengths, and we want to keep the access as sequential as much as possible to reduce the to get more data transfer per seek. And IO schedulers are designed to do that. And when in the situation we have multiple processes in a system all generating IO streams, processes tend to generate localized IO. So a process is accessing a set of files. Those files are typically contiguously located on the disk. And so a lot of the IO has a lot of locality. So a process tends to generate IO with a lot of locality. But when you have multiple processes running, we get multiple streams of locality. But by the time it gets down the drive, by the time it gets down to the scheduler, it looks pretty random as they're interleaved. And the scheduler de-interleaves those and presents them to us in groups that improve our performance. Schedulers take a lot of different approaches. Deadline scheduler, the most common scheduler, prioritizes reads, holds writes to a deadline. And then we have fair schedulers like BFQ, which help to make sure that processes are allocated a fair portion of the bandwidth. And then other combinations of scheduling algorithms, which are half engineering and half magic. Next slide, please. So let's talk about BFQ. And this is some work that we're working on currently. BFQ is a complex scheduler designed for hard drives. How BFQ works is on this chart, you got these signifies these processes at the top, and at the bottom there is a dual actuator hard drive with an upper and lower actuator. In this case, it's a SATA. So it has a 32 command deep queue. 32 commands is not a lot of, it's not a really deep queue. And as opposed to a Seagate SAS drive, that's 128. But with 32, it's easy for a process to generate a burst of IO that resolves to 32 or more requests down to the storage device, down to the drive. And that is the key of what has to happen at the IO scheduler to keep a single target multi-actuator drive like this happy. This diagram kind of shows a unfortunate workload case where we have processes P1, P2, and P4 are all generating IO that's destined for the lower actuator, and P3 and P5 are generating a mixed load. How BFQ works now with the modifications that we've made to support this is BFQ establishes a queue for each process and for each actuator. And then BFQ has this queue arbitration and servicing function below that makes sure that these queues are fairly serviced. And the goals of BFQ are to make sure that no process has to wait too long, and each one of these queues is sorted and managed for optimal performance. And since it's fair, then it calculates a heuristic per process to make sure that the arbitration and allocation among the processes is fair and even. And ultimately, everybody gets better performance out of the limited capabilities of the storage subsystem. What we did to make sure that the actuators stayed busy was to recognize that as this queue servicing algorithm works its way across these queues, you can see that as it's working its way through the processes and through the queues, as it's working its way through P1 and P2, there really aren't any red commands destined for the upper actuator to be done, to be dispatched. If you just let it run like this, then the upper actuator will run out of work to do and go idle. We don't want that to happen. We want the actuators to stay busy. What we know about, for example, a SATA dual actuator drive like this is that of our 32 commands that we can have in the queue, for sequential workload, we really need 2 to 4 commands in the queue. Anything more than that in a sequential workload is excess. We can maintain full sequential performance with somewhere between 2 and 4 commands in the queue, depending on the system overhead and the transfer links. For random, it's well known that deeper queues give you higher performance because the average sync length, the drive sorts and the average sync length goes down. So we like to keep the queue full for random, but what BFQ takes advantage of is the fact that we can, so in the case where the queue is monopolized by a process that is generating a lot of IO, we can steal a few of those queue slots and assign them to the other actuator. So in the case where we're doing random workloads, in the case where both actuators are seeing random workloads, we can steal 4 slots, 4 of the 32, and assign them to the lightly loaded actuator and get about 75% of the raw random performance that you get of a deep queue. For sequential workloads, 4 is always good enough for full disk rate. So what BFQ does, between dividing all the commands up per process and per actuator, it monitors the commands that are in the hardware queue, what actuator they're destined for. And if one of the actuators' number of commands in the queue drops below a threshold, which we have set for 4, then it will inject some more work for that actuator as long as it's available. This is a really important distinction on load balancing and load management for multi-actuator. The IO scheduler does not redistribute the load over the actuators. The IO scheduler's job is to ensure that if there's any work anywhere in the system queues for an actuator, that the actuators stay busy. If there's no red in this picture, no work for the upper actuator, we are not going to redirect lower actuator work to the upper actuator. But if there's any commands at all, any requests at all in the system for the upper, then we're not going to let the upper go idle. And same thing for lower. By not letting the actuators go idle, we picked up a big performance advantage because without this active intervention, it was such a shallow queue depth, it's very likely that an actuator runs out of work to do and goes idle temporarily. Next slide. There are about 1,000 different ways to present a block device under Linux, between all the Devicemapper targets, partitioning, and there are a lot of them are religious in that, we have our favorites that we're comfortable with. And so I'm not going to try and exhaustively go over all the pros and cons and ways to do this, but I wanted to give you some food for thought on how to manage a single target multi-actuator drive. First of all, you can just plug it in. The IO commands are the same. Nothing is different. You do an IO to a sector, to an LBA, just like you always did. And the drive is the only one, when it comes in, the drive looks at it and it knows where in the pack, in the disk pack, that sector belongs, and it knows which actuator can reach it. And it takes care of that for you. You don't have to tell it. So you can plug a drive into your system, a SATA dual actuator drive, and it'll run just fine. And if your workload that you happen to be given it has enough variability where it's covering enough of the span of the address space, you'll get good performance too. But most of the time, we really want to actively manage where the IO is going. And so, like, the simplest way that everybody knows how to do is partition the drive. You partition it at the actuator boundary, and those two partitions, show up as two different partitions in your system. then you can build file systems on them or consume them raw, whatever you need to do. Linux does not manage queue depth per partition. Linux manages queue depth per device. So everything we talked about before on BFQ, where workload to one actuator can monopolize the queue and cause a denial of service to the other, is true with this scheme. So the fact that we partition this drive, if we direct a bunch of IO to partition 2 on this slide, then we can monopolize the queue with partition 2 easily with SATA, because it's only 32 deep, and cause partition 1 to go idle. So the partitioning scheme, and in fact, any of these schemes we're going to talk about under SATA still have the exposure to queue monopolization in an idle actuator. This is a fine way to do it. And it's easy for any Linux administrator, even a beginning Linux administrator, to understand and manage. And it has the capability of giving just fine performance. You got to bear in mind on these schemes that these two actuators, for all intents and purposes, are in the same failure domain. There are a few failure modes on the drive that affect only one, but I've been advising our customers not to rely on any of those single actuator failure modes, and to consider any data on anywhere on this drive to be in the same failure domain. Next slide. The Linux administrator, after he understands partitioning, then the next chapter is the Devicemapper. And the Devicemapper is a miraculous piece of software down in the lower part of the stack that mechanically separates these, by strict mapping, creates multiple new block devices out of an existing device. So this is the simplest of them, the linear Devicemapper target, and it makes it very easy to divide this device up into two block devices. There's no partition table involved. This is not a partition drive. You can, but you don't have to. But the Devicemapper is really more of a tool, because I don't think most people deploy the Devicemapper directly. We get the next slide. We'll talk about LVM, which is a convenient way to manage the Devicemapper. But you can see here is that it's really straightforward. That by configuring the Devicemapper, you can take this linear array of LBAs and split into two, and come up with two devices. Everything we said about partitioning is true with this. If you apply a heavy workload to actuator 1, you can monopolize the queue and lock out actuator 2, because Linux does not control queue depth per mapper target, controls it per device. Next slide, please. LVM2 really is the Swiss Army knife of managing storage, and it gives us, with a split LBA approach, single target split LBA, where half the address space is to one actuator and half is to the other, gives us LVM2 gives us everything we need to set up any kind of storage arrangement above it. This is no different from using LVM2 on any of the drives that you're used to doing, except that our intentions are a little bit different. Is that we want to expose volumes that have some meaning to the actuator arrangement below it. So we can do them striped and stripe it across two actuators. We can bust the actuators out independently in linear volumes, whatever. It's an extremely flexible system that can do whatever we need to do, including combine more of these if we wanted to, more of the multi-actuator drives into a single or multiple volumes. Probably most of you are familiar with a lot of the LVM2 functionality, and dual actuator doesn't change any of that functionality. But dual actuator gives you one more aspect of the drive behavior to manage using LVM2. Next slide, please. We're going to talk a little bit about performance. Next slide after this. And talk about, this is kind of, a lot of this is Seagate implementation driven, but I wanted to go over what the performance expectations would be for multi-actuator. We like to say it's 2x, but it's not. It can be darn close to 2x. For two sequential workloads, it's 2x. For two random workloads, it can be about 1.8x. Some of this is I think inherent in the design challenges of the device. Some of it's inherent in the design decisions that we made, and some of it is maturity. We optimize the drive. Next slide, please, Ari. First, we optimize the drive really to work at low Q depths, random, and sequential workloads. That's because the initial customer adoption for this product was content delivery, where we're running multiple streams, and sequential performance was exactly what they were looking for. And for email, where we needed the IOPS. The customer wanted the IOPS and definitely was interested in IOPS per terabyte. So for sequential writes, the performance results we have seen is that at low Q depths and short transfers, our performance is limited by, and this is nothing unusual with this drive, is the command turnaround from command to command, and just overhead in our system and on the host. And we see a departure from 2x on this with a slightly lower performance than 2x. The design, that the Seagate design has a dual, since the hardware is duplicated for each actuator in each channel, it's parallel and duplicated. Eventually they have to come together at the interface. And so we have the potential for the two controllers to have to wait on each other. And so for short transfers, we can see it impacting the performance. However, once we get some commands in the queue, we get the transfer size up, sequential performance is really good. And we will run it at disk rate to simultaneously to both actuators, particularly with 12 gig SAS. Yes, 6 gig SAS, even though 6 gig SAS provides enough raw bandwidth, we are close to the theoretical maximum throughput, and so we're real sensitive to SAS bus scheduling, and it's possible with some host systems to see a departure, to see a drop off with 6 gig SAS. 12 gig SAS has done well for us on this. It's an interesting side note is that these two LUNs, or the two actuators, don't have identical performance, because like any other, like all disk drives, each head disk combination is optimized for its best performance, and some head disk combinations are more capable than others. And on the, so you got a drive that's 250 megabytes a second OD data rate. That's average, and some heads on that drive, some head disk combinations were delivered 270 and some 240. And so as you see, as you work like any drive, as you work your way across, you can see variations in sequential throughput. And so since the two actuators have different heads of media, you can see different performance on the two actuators as well. But ideally, we expect to see the performance to be the sum of the two at any given place on the media. Next slide. Some drive design facts here is why do I say that Harrier is optimized for shallow queue depth workloads? Because this is a split actuator design. The two actuators are on the same shaft, the same pivot. And there is even though mechanical engineers did a great job and spent a lot of time working on this, there is some mechanical coupling between the two actuators. And that mechanical coupling is the main source of that is the acceleration and deacceleration portions of the seek. A hard drive seek has an acceleration, a coast, then deceleration. And depending on the seek length, is how much for a given seek, how much of the actual seek time is spent in each one of those ranges. To keep the mechanical coupling between the actuators manageable, the Seagate design that we have right now has slightly softer acceleration and deceleration. Although the ultimate velocity is still the same. So what that means is that for medium and long seeks, the drive performance is comparable to a single actuator drive. But for the shortest seeks, which are dominated by the acceleration, deacceleration profiles, they're slightly slower. That's why for high queue depths, which cause shorter seeks, we do not see the full 2x performance delta. But for low queue depths, which generate longer seeks, or for sequentials, which aren't concerned with seek performance, we do. We're never slower than a single actuator drive. No, when we say we're seeing a fall off in performance from 2x, talk about 1.8, 1.9x, where we would like to say it's 2x all the time, but it's not. Next slide, please.
Yeah, Tim, we're getting close to finishing up on time here, and I think we're getting close to the end of the performance talk. So do you want to wrap it up, or do you want to continue on with these last few slides?
I'm okay with wrapping it up.
Yeah, I think we really covered what we wanted to here. We'll leave the slides up for folks who want to follow up offline, but these are the main lessons learned right here. You obviously want to maintain work balance between the two actuators. There's a lot going on here. Q depth's important. Watch your metadata overhead. There's IO dependency between actuators. And Tim, go ahead and butt in here if you've got more color. And we're driving towards 12 gigabyte SAS, gigabit SAS, which, as Tim noted, we're butting up against the limitations of 6 gigabit.
Yeah, dual actuator is more of everything, and dual actuator stresses, when you got a step, double your sequential data rate essentially, and practically double your IOPS. What we've learned is the other parts of the system, need to increase too. You need more SAS bandwidth. You need slightly more power. You need more processes to keep these drives busy. So, the things that these lessons we've learned is that that big step changes in drive performance require some adjustments other places in the stack. That's really all we're saying, and they're not complicated adjustments, and they're totally within the capability of nearly any Linux storage administrator once they understand the concepts and what drives the performance parameters on these kind of drives. So, like I said at the beginning, I've been with this from the beginning. I really believe in the technology. I've been doing disk drives for 30 years. I know other people have done multi-actuator before, but the technology is ready now, and the capacities are big enough now to make it worthwhile. And I think we're going to see a lot more of them.
Oh, thank you, Tim. And for the audience, thank you for attending. We have a Slack chat, and Tim and I will be on hand to answer your questions and have any discussions you want to have. And please take a moment to rate this session. Thank you.
Thanks.